Now we're going to do the second problem from lecture today. And let's just read through here. We have a rigid bar. Let me raise this up a little bit so you can maybe see all of it. Okay, we have a rigid bar BCD, which is supported by a pin at C and an aluminum rod 1 from A to B. We're going to apply a concentrated load to the lower end of aluminum rod 2, which we're going to call DE, which is attached to the rigid bar at D. Okay, then it gives us the cross-sectional area of the rods, both of them. After the load is applied at E, the strain is measured in rod 1 as 900 microstrain. Determine P, the total deflection of E, the shear force acting on the pin at C, size the pin, assume single shear. Okay, so we have a lot going on here. So it's important to note that BCD is rigid. That means as I rotate, there's no deformation in this angle. It's going to rotate at point C. So when I apply a load at P, I'm going to start here and work my way through the system. As I apply a load at P, I can see that DE is going to have this force of P acting through it axially. So I'm going to have some deformation just because I have stretching of the rod from D to E. So if I'm looking at the total displacement of E, okay, the total displacement of E to E prime, it is going to, number one, come from stretch of rod DE by the applied load. As this load works its way up to the pin here at D, we're going to have some rigid body rotation. So I'm also going to have the displacement of D to D prime, we want to call that D prime, just by the rotation of the system. So there are two things that are going to be affecting this displacement at E. So I like to organize my information. I pulled this out of the back of your book just so that we would have all the information right here. And we are going to look at, we're going to call them rod AB and DE, and they are the same material. So we can just go ahead and write out that our yield stress is 40 KSI. And that's important to note because we are assuming if we are using this modulus of elasticity, we are going to be in the elastic region still as we are doing rotation, which means after we unload, everything goes back to the original position. So we have our modulus of elasticity of 10 times 10 to the third KSI. Make sure you're reading those units correctly. We have Poisson's ratio of 0.33 in case we want to look at change in diameter. We have a shear modulus of 3.8 times 10 to the third KSI. So if we wanted to look at shear properties, and I went ahead and looked at yield stress for this material, and I got 30 KSI from another source. Okay, that yield stress, the shear, is not written on here. Okay. So here's our information. We also have the length initial of AB is 50 inches, and the length initial of DE is 100 inches. They both have the same original cross-sectional area of 0.20 inches squared. And then the other thing that we can note is that we have this microstrain of 900, which is 900 times 10 to the negative 6 inch per inch. So far, the only thing we know that's different about our loaded system is the strain that happens in this cable. Okay. So before I get started, I like to just go ahead and draw out my free body diagram. So if I'm looking at equilibrium, this is what we would see from statics. I have a load P, which is acting through that cable. I have tension, which is the force in AB, and I have a pin here. So I have CY and CX. This is 20 inches tall, 30 inches to the side. Okay. I'm also going to look at my deformation. So I start out and then I rotate. I have rigid body rotation, so it stays at 90 degrees. And if I have a delta of my cable AB. I also have a displacement of D to D prime. We're going to just call that delta D. As I load this cable up, okay, as I load my cable, so here is cable DE, I know that as I load that, I'm also going to have a delta D to E that's caused by this force P, which is going to equal that force that's in my cable DE. Okay, so as I'm looking at E prime, my final position, it's going to come from both the delta due to the load and the delta from rotation of my system. So let's start with the spectrum. We kind of touched on this in class. I know stress is P over A. I know that stress is related to strain. I know that strain is change in length over length, which is length final minus length initial over length. And I know that Poisson's ratio gives me that lateral strain, which is cross-sectional to longitudinal. If I want to be specific, this is longitudinal strain because we're applying a longitudinal load. And honestly, I need to look at rod AB. So I really have a stress in rod AB equals the force in rod AB divided by the area of rod AB. So the stress in AB equals the modulus of that material times the strain that's happening in AB, et cetera, et cetera. If I'm looking at rod DE, I have the stress in DE, which is the force in DE divided by the area of DE. I have stress equals E times strain. And I would need to maybe think about doing this for all of my materials involved. So the first thing I want to find is the magnitude of load P. And I know that P is related to the force in my cable using equilibrium. But I don't know what this value is. I do know, however, that I have a strain in my deformation of 900 times 10 to the negative 6 inch per inch. So if I know the strain, okay, and I know the material, well, let's look at our information here. If I know the strain and I know the material, I can actually find the stress that's in cable AB or rod AB. If I know the stress that's in rod AB and its area, I can actually find the force that's in rod AB that caused this strain. And if I can find the force in rod AB, I can go back to my statics equilibrium free body diagram. I can sum moments about P and calculate the force that started it all. Okay, so let's look at A. We want to find the magnitude of P. So we're going to have to start with rod AB because it's the only thing we have information on. And we know the microstrain is 900 times 10 to the negative 6 per inch. Okay, and I know that stress equals E times strain. Okay, and we have everything in our table. So I have 10 times 10 to the third KSI times 900 times 10 to the negative 6 inch per inch. Okay, and I can multiply this out and I get, where's my calculator? 10 times 10 to the third times 900 times, and I get that the stress in AB is 9 KSI. And what do I know about stress? Stress equals the force in AB divided by the area of AB. So I have that 9 KSI equals force in AB divided by the area. I can go back. I have my original informational chart. That's why I like to have everything organized so I don't have to read over and over. And I have 0.2 inches squared. So I can take that 9 times 0.2 and I get that my force in cable or in rod AB is 1.8 kips. and I need to be careful I'm using correct units. So I have inch squared, I have inch squared, things are good. So this tells me the force in AB. So guess what I do? I'm going to go back over here to my equilibrium equation, just like we did in statics as we figured things out. And I'm going to put 1.8 kips. And now that I know that, I could actually sum the moments about C, which is my pin. And if I can sum the moments about C, I have 1.8 kips times 20 inches minus P times 30 equals 0. So we have 1.8 times 20. We have 36 equals P times 30. So P equals 36 divided by 30. And I get 1.2 kips. So this P is 1.2 kips. That's what started it all. So there is my answer for part A. P equals 1.2 kips. Now I want to know the total deflection of point E relative to its initial position. And that's where I have to understand, not only do I have a delta because of rotation, but I'm also applying 1.2 kips to, okay, to my system, and it's originally 100 inches, so I'm going to have some stretch because of that. Okay, so let's move on here. We're going to draw a line so we know we've moved on to the next. And delta E, okay, to E prime, whatever you want to call it, is going to come from rotation. So that's going to be D to D prime plus elongation. So how do I find the rotation? I can use similar triangles. I can go back to my deformation free body diagram and find that very quickly using similar triangles. How can I find elongation? Well, that's just delta because of the force. And so I know that stress is force in dE over area. I know the force, I know the area, I can find stress. If I know stress, E times strain, I can fill in, use my material properties, find strain, and I know that strain is delta over L naught. Okay, so again, we're working through our spectrum of equations. So let's start with similar triangles. So here's my picture. Delta A, B, D to D prime. This is 30 inches. This is 20 inches. Okay, delta. Well, I was given this microstrain, and how is microstrain related to delta? Strain equals delta times L. So I can actually multiply that microstrain by L to get the delta, which is the change in length of rod AB. Okay, and similar triangles. Delta AB is to 20 inches as D to D prime is to 30 inches. So let's go back and work on that. So we have delta of AB is to 20 inches as D to D prime, that's the rotation, is to 30 inches. And delta, strain equals delta over L. So delta is that original strain that we were given of AB and the original length of AB. So we have 900 times 10 to the negative 6 times our original length of AB, which was 50 inches, is to 20 inches. This is where the similar triangles comes in, as D to D prime is to 30 inches. So I can cross multiply, divide by 20. So I have 900 times 50 divided by 20 times 30, and I get 0.0 D to D prime. Let's recheck that math. So I have 900 e to the negative 6 times 50 inches divided by 20 inches times 30 inches, 0.0675 inches. And what is that telling me? What that is telling me that D, as I rotate, is going down by that amount. 900 e to negative 6. Enter. Okay. So that's the first part of this, elongation. Okay. Stress equals force over area. I know that at P, I'm applying 1.2 kips divided by 0.2 inches squared, and I get 1.2, 0.2 divided by, I get 6 KSI. And how is stress related to strain? Stress equals E times strain, so 6 KSI equals 10 times 10 to the third KSI strain. So when I divide, I'm going to get strain is 0.0006 inch per inch. And what is strain? Strain is change in length over original. So if I want to know the stretch in that rod D to E, I can take the strain, multiply it by the original length, and I get 0.06 inches. So as I'm looking at that displacement of point E, okay, it's going to be the displacement from the rotation plus the displacement due to the force in the rod. And there we go. 0.0675 inches plus 0.06 inches. And if I add those two things together, I get 0.1275 inches down. Okay, so that answers, I believe, part 2. Now we want to know the shear force acting on the Penancy. Well, remember the shear force is actually the magnitude of the force on the pin. So we need to find both the x and y component, use Pythagorean theorem, that we can find then the magnitude. So let's go back and look at our equilibrium equation. So if I sum forces in the y direction, I'm going to find that Cy is 1.2 kips. If I sum in the x, I have 1.8. Okay, so those are both large numbers. Please don't just pick this and call that the actual shear force, because the shear force is the magnitude of 1.8 squared plus 1.2 squared. And we get 2.16. That is the shear force acting on C. It's actually the magnitude, and I have to take both the components because our components don't just magically break up. So if I wanted to find that shear stress on C, okay, I know that, whoops, this is not shear stress, this is actually force. I know that the shear force is 2.16 kips. Okay, so our shear force on C is 2.16 kips. Now, if I want to size my material, I have to start thinking shear. Shear stress is G times shear strain. And I also know that shear stress is the shear force over cross-sectional area. So if I know that my force is 2.16 kips, and I know that my allowable yield stress is 30 KSI, I can say that 30 KSI equals 2.16 kips over cross-sectional area. And I can cross multiply, so area is 2.16 over 30 kips, KSI, and I will get a value in inches squared. If I know that it's a pin that's round, it's pi over 4d squared equals area. So I can keep back calculating to find that dimension. Okay,